Hi, in today's video, we're going to take a look at this DS4T1012 handheld oscilloscope from DreamSourceLab. It is a touchscreen operated, dual-channel 150 MHz bandwidth, 1 GB samples per second digital oscilloscope and has a whopping 16 megapoints of waveform storage depth. Besides these already impressive specifications, it also supports protocol decoding, in-depth FFT spectrum analysis, and it even has a built-in function generator. I'm definitely very excited to review this little device, and I'm sure you would be interested in learning a little bit more about this handheld oscilloscope as well. And of course, we'll do a teardown later in the video, and I always try to do that whenever it is possible, so be sure to stick to the end. Now, quite a few of my viewers had asked me about this scope in the past. I did not have one, but I looked at DreamSourceLab's website and found the specifications very promising. So I reached out to them to see if I could do a review of their DS4T1012. And they were very responsive to my inquiries and provided me with this unit. I'll provide a link to their website in the video description below so you can check it out for yourself. And I believe you can also order it directly from their website as well. The scope came in this rather long instrument carrying case, and it was actually shrink wrapped and placed in the carton box for shipping. I'll put an unboxing clip in the corner up there in case you are interested. Anyway, let's see what comes with this oscilloscope. As you can see, here is where the scope sits in the box. It's right in the middle, very well protected. And underneath the scope, there is a quick start guide. You can see here, let me just take it out. And the quick start guide is actually very clear, and you'll definitely be able to use most of the functions of the scope after reading through this quick start guide. And you can also download the full manual from DreamSourceLab's website, which contains 60 pages. The manual is very well written and definitely worth spending some time reading through, as there is a ton of great information there. One of the reasons the case is this long is because it also comes with a couple of standard oscilloscope probes, and they're in this separate zipper compartment. Let's check them out here. Let me open it up. So the probes DreamSourceLab supplied are these 200 MHz probes. P2200, 200 MHz. And they're actually of pretty good quality here. And let's see what else is here. You also have some probe accessories by the look of it. Now, I really appreciate the use of standard oscilloscope BNC connectors, as some of the portable oscilloscopes of this size did away with BNC connectors. Some of them, like Miniware, for example, use MCX connectors for the probes. Although that saves some space, it makes the probes non-standard and non-interchangeable, which in my opinion is not ideal. Let's see what else we got. And because this scope also comes with a built-in function generator, you also get this MCX to BNC cable by the look of it. And the reason they chose to use the MCX connector for the signal generator output is because, as you can see here, the scope just doesn't have enough space on the side. And we only have extra space just enough for this MCX connector here. Also, the signal generator is not the primary function of this device, so I think this is actually a good compromise. And of course, you have a USB cable to connect your scope for charging and to the computer. Anyway, this scope is actually very tiny compared to many of the portable scopes that I have reviewed before. Now, for a size comparison, here I have a Finersi DP-OX180H, which I just reviewed a few weeks ago. And here I have an O1 HDS 2202S that I reviewed a while ago as well. So you can see here, by comparison, you can see just how small the DreamSourceLab's oscilloscope really is. Yet, it has the largest LCD among these three portable oscilloscopes, as the touchscreen on this DS4T1012 is 4.3 inches. Also, you can see here, we only have a few buttons on this DS4T1012. Besides the power button on the side, we only have two buttons on top. One is for run and stop by the look of it, and the other one on the right is for the auto acquisition. The case is rubberized and definitely feels very secure in your hand. For devices like this with very few physical buttons, the touch interface has to be top-notch. Otherwise, users will get frustrated very quickly. So let's power it on and take a look. And by the way, the very first time you power on the device, it will ask you to select the language, as you can see here when I powered it on initially. Oh, before I forget, the DS4T1012 also has a stand that gives you a couple of inclining positions. You can see one is here and the other one is further out. You can put it on the desk like this or like this. But for this video, I'm not going to use a stand, and I'll just simply put it on its back, as that's the easiest for me to operate the scope while shooting the video. Because the screen is glossy, you can see there's a lot of reflection. I think I'll have to turn off my overhead lights, as otherwise you would see the reflections on the screen, which would be very distracting. So let me do that first. It seems there's still some glare on this side, but I don't want to just turn off all the lights just yet. So let's take a look here. All right, let's power it on. Wow, did you see that? That was not even a second. This is probably one of the fastest boot up time I have seen among portable scopes that I have reviewed. Let's try it again. Oh, actually, I was too excited. I didn't realize that I haven't removed the protective film just yet. So let's do that first. Actually, without the protective film on the screen, it seems that the reflection is actually less. Anyway, so we'll see how it goes. Alright, let's do it again. That was just beautiful. The sound is also soft, not like those ear-piercing beeps we routinely found in some other devices. So the fast boot up time suggests that this scope is not using a traditional operating system at all, as the boot up time of an embedded OS can take half a minute or even longer. Anyway, this is a really good start. I like it. By default, the trace is stopped, as you can see here. This is a little bit different than most of the scopes, but you have the flexibility to change the power on behavior. You can set it so that it remembers the prior state, and we'll probably take a look at that setting later if I remember to show you. You can either use a run stop button located on top here to start the trace, or you can use the on-screen button here to start and stop the trace. It achieves the same result. On this oscilloscope, there are usually multiple ways to get to each of the settings, which is a great design in my opinion. You will see more of that later. And also, right now you notice that only channel 1 is enabled. You can turn a channel on and off by just tapping on the probe area. There is a slider button here. I don't know how well it shows up on the camera here, but anyway, you can tap it. The channel 2 is turned on, and I can tap it again. The channel 2 is off. Now, the colors of the traces are slightly different than your traditional scope. Instead of yellow and cyan, it's pink and green. I'm not too wild about the color choices here. I actually like the default yellow and cyan, but don't worry, you can change it. So let's do that first. So let me show you how that is done. I press the channel here, and you can see color. And let's see. So for channel 1, we want it to be yellow. And that's it. And for channel 2, let's change it to cyan. And now, actually I can't see if that's cyan or blue. I think it's this one, cyan. Now that sets it to the standard color scheme. Besides changing color of the trace, you can also set the bandwidth limit. You can see here, I can set it to 20 MHz, or I can leave it as full. And also I can change the probe attenuation. You can see here, I can change it to 5x, 50x, so on and so forth. Let's change it back to 1x. Now, this is actually not a real attenuation, by the way. You need to set it to the attenuation of the probe you are using so that the reading would be the correct value. You can also change the AC-DC coupling here. Very easy. One thing comes in handy is that you can switch the measurement unit between voltage and current. For example, right now the default is voltage, and if you are using a current probe, it will come in handy if you change this to current, so the reading would match the current reading instead of voltage. So as you can see already, the menu is very intuitive. And just a few other things I wanted to point out. If you tap on the logo here, you will see this About menu. Looks like the latest version is 0.99, which is what we have here. And here is the language menu that we actually set that when we initially powered on the unit. But in case you chose the wrong language to begin with, that's how you set the language here. And up in this corner, if you tap it, you can adjust the backlight and sound. You can turn the sound on and off, but I think the sound level is just about right, so I will leave it on. Now let's put a signal into channel 1 and take a closer look. For this test, I'm just putting in a 1 kHz 1 volt peak-to-peak square wave signal. And there are multiple ways for you to auto-acquire the signal. Remember, we have a physical button labeled auto up here, and we can press that to acquire the signal. Alternatively, of course, you can use the auto set to acquire the signal as well. Now let's turn off the channel 2 first. To change the time base manually, you have a couple of options as well. You can press the upper half, for example, to increase the time base, or you can press the lower half of the screen to decrease the time base. Or there is a single hand operation mode, which you can activate by press and hold the white space to the left, and you can see here we can change the horizontals, and then you can use the scroll wheel to scroll up and down to the desired settings you intended. I think the designers had really put a lot of thought into the different use cases here. Now, changing the amplitude is just as easy. You can press the volt per division here, and you can see it started flashing. Then you can use up and down to adjust the amplitude, or you can simply pull up the menu here, and you can kind of adjust it right on the menu here. There's a scroll wheel. Or you can use one-handed operation like we used earlier, and you can see here we have a up and down adjustment, and then you can adjust it up or down. So very similar to what we did before. One thing implemented on this scope you don't typically find on many other scopes, even benchtop ones, is the overrange indicator, and I can show you here. So let me adjust the verticals. And you can see as soon as we exceed the vertical display, the out of range message came up. The overrange indicator is very useful, especially when dealing with an unknown signal. When you see this indicator, it means that you need to reduce the vertical amplification so that the signal is within range. To position the waveform is just as easy. You can press the channel indicator here and it will turn solid, and you can move it up and down. Or you can move up and down the screen here. It will show you the predefined positions, which is very handy. Or you can use the on-screen predefined positions to set it to the upper quarter or lower quarter. Or you can just set it in the middle. Anyway, as I have demonstrated here, the basic operation is very intuitive and easy to use with this touch interface. Definitely hats off to the designers of this oscilloscope. Doing measurement on this scope is also very easy. Let me just quickly demonstrate here. So let's go to measurement menu. You can see we can add different measurement parameters. Let's do frequency, and let's add another one. Let's do peak-to-peak voltage. And you can see we have these two parameters displayed on the screen. And if you want to come back, change it. For example, I want to remove all of it. Simply just click that button and everything is gone. We can also do cursor measurements with this menu. So let's take a look at that as well. So let's do horizontal. And let's come back here. So I just press the cursor. Let's move it down. And let me move it up. You can see just how easy it is. We get the 1 volt right here. And let me also add a vertical cursor here. So let's go to measure, vertical bars, and come here. Let's go, let's see, start from here. And we want to end at 1 cycle, roughly here. And you can see we roughly get that 1 millisecond duration here. So again, the operation is very intuitive and very simple. So let me remove those measurements here. Now let's verify its bandwidth claim. The scope has a 1 gig samples per second real-time sampling rate for single channel operation, and it drops to 500 meg samples per second for dual channel operation, which is very typical for a single ADC architecture, which we'll have to verify in our teardown later. And the specified bandwidth is 150 MHz, which is very good if it can achieve that. So let's verify that with my HP8642B humming in the background. For this test, I have connected a 50 ohm through termination adapter at the oscilloscope's input, so we match the output impedance of the RF synthesizer. Let me first test with just a single channel enabled. And as you can see here, we're currently outputting a 50 MHz signal, and the amplitude is at roughly 200 millivolts RMS. So let me first increase the frequency to 100 MHz. And now we're at 100 megahertz. We can actually reduce the time base a little bit more. And in fact, this one even has a 1 nanosecond per division, which is really impressive here. So let's change it to 2 nanoseconds per division. And you can see the amplitude roughly stays the same, and the frequency measured here is 100 megahertz. So let's increase it to 150 megahertz. And the amplitude actually increased a little bit. I wondered if there is some kind of internal calibration constants based on the front end it's currently measuring. But anyway, so right now you can see we are able to measure that 150 megahertz, and the amplitude right now is sitting at 250. But let me reduce the amplitude a little bit so we can see the signal a little bit clearer. And the choir signal looks actually pretty clean here. So let me keep increasing the frequency here. So let's do 175. And you can see the measured waveform is a little bit wobbly now, but we are still able to get that sinusoidal displayed on the screen here. Let me keep increasing. Right now we're at 200 megahertz, and let's change the trigger a little bit to see if we can get it a little bit more stable. And you can see we can measure that 200 megahertz with no problem. So let's keep increasing. And right now we're at 250 megahertz. And we do see some offset on the screen. So clearly there is some issue. Also, you notice the amplitude measured here dropped to 115. So let's actually reduce the frequency a little bit to 225. And it seems like for a single channel, we can reliably measure up to 150 megahertz for sure, and we can stretch it a little bit. Right now we're at 225 megahertz, and you can see we can still measure the signal with reasonable amplitude. And right now, the actual amplitude dropped to about the 3 dB bandwidth. You can see it's 150 roughly. Of course, at this frequency level, you can see we have a lot of artifacts. The measured waveform may not be as useful, but of course, this is way outside the 150 megahertz claimed bandwidth. So just to illustrate that, indeed, we are able to measure frequency at least up to 150 megahertz. Now I have changed the output frequency back to 150 megahertz. But let me actually reduce the amplitude here. With both channels enabled, you can see right now the waveform on channel 1 is a little bit of a wobbly here. Let's actually move channel 2 up a little bit so we can see it a little better. And the degradation of the signal quality is somewhat to be expected, as right now we are only running at 500 megasamples per second versus the 1 gigasamples per second sampling rate a while ago with a single channel operation. So let me increase the frequency a little bit. So now we're at 175, and let's do 200. So it seems that we are actually able to acquire the same frequency signal as in the single channel operation. It's just the signal quality is a little bit worse than what we had before. So let's go to 225. You can see that we captured that signal with no problem. Here I'm showing an amplitude modulated signal. It's a 1 MHz carrier with a 1 kHz modulation, and the modulation depth is 100%. Now, it can be a little bit tricky to capture a stable AM signal, especially on cheaper scopes, because there's not a whole lot of triggering options to work with. But for the DS4T1012, you can actually see the triggering capability here is pretty comprehensive. You have the ability to trigger on rising edge, falling edge, and even adjust the triggering sensitivity, but also, more importantly, we have this hold off function here. So we can add some hold off. So you can see now, we should be able to trigger a very stable modulated signal here. What you're looking at here is a frequency modulated signal. The carrier frequency is again 1 MHz, and we're applying a 100 Hz modulation on top. The frequency deviation is 100 kHz. You can see how fast the scope's update rate is. And next, let's take a look at the single shot capability here. For that, we're going to measure the power-on characteristics of a switching power supply. And to enable single shot is very easy. All you do is you press this single button. You can see that this is essentially single shot enabled, and now we're going to start. So let me turn on the output. And you can see we have captured the power-on characteristics of that switching power supply with no issue. Let me increase the time base and we'll do it again. As you can see, we capture that waveform beautifully. And single shot is where the memory depth comes into play, so you can actually zoom in the signal and see the details if you'd like. And of course, you can adjust the sampling memory depth, and for that we can come here. You can see currently we're at 2 megapoints for a single channel operation, and we can change it all the way to 16 megapoints. Of course, it will clear the signal, but you get the idea. So let me set it back to default. The FFT functions on most of the entry-level scopes are pretty rudimentary, but on this scope, you can actually do quite a bit of analysis with it. So again, right now we're measuring a 1 kHz square wave signal. Let me turn on the measurement so we can see that frequency. And you can see that's a 1 kHz signal. And now let me enable FFT. And as you can see here, we can apply different windows on top of the FFT. And let's apply a Henning window. And let's hit OK. And right now, we are not doing much just yet. Let's come to the FFT channel. And let's see what we're going to do here. So we're going to measure the center frequency at, let's say, 1 kHz. And let's actually place some cursor on top. So here's our cursor. You can see we can use that to measure the frequency. Now, this is actually, the scale right now is too wide, so let's change it again. So let's come back here, and let's do this. Instead of 100 times, let's do from 1 kHz to 10 kHz. Now let me enable the cursor. So now we can use that to measure the peaks. You can see that the first peak is roughly at 3 kHz. And you can definitely play around with the FFT a little bit more, but that just shows you the capability of the FFT analysis. Now I have removed the Henning window. You can see the shape of the spectrum had changed. Of course, there are some functionalities you don't have. For example, we cannot fine-tune the frequency resolution, but it already gave you a lot more capability than your typical oscilloscope in terms of FFT analysis. Alright, now let's take a look at the Lissajous figure measurement. For that, I'm inputting 2 sinusoidals at 1 kHz. They are 90 degrees apart. So let's enable the XY mode. And you can see we get a perfect circle here. So let me change the frequency of one of the channels. And you can see the update rate is really fast, which is excellent. And the beauty here is you can actually swap the 2 channels. For example, if I wanted to rotate the Lissajous figure, all I need to do is essentially swap X and Y. Of course, you could always swap these 2 inputs, but this gives you the additional flexibility here. And this feature is really a nice touch. Next, I want to test out the protocol decoding capability. But before I do that, I wanted to adjust the probe compensation here using the test signal output. So let's do that. And that looks about right. The DS4T1012 can decode UART, SPI, and I2C. So now let's actually try decoding a UART signal coming out from this Arduino test board. So let's go to More. And the I/O here is our protocol decoding. So we do UART. And the baud rate, I think I set it at 9600. And that should be it. Of course, we're on channel 0 right now. Actually interesting, they call it channel 0 and channel 1. We typically call it channel 1 and channel 2, but that's just something minor here. Let's hit OK. And now you can see the decoded signal. So let me move that here. Down here. And let's see if we can change the display here. So ASCII view. And let's zoom out a little bit. And now you can see the test is essentially outputting hello world. Very nice. I think right now we're using the default sampling depth, so let's double check that. Yeah, so now let's increase it to the full 60 megapoints. And now you can see that we have a visual indication that the memory depth has been increased because the green bar essentially narrowed a little bit. That means we have more sampling depth. So the protocol decoding capability is definitely very useful. Now let's try to capture the waveform of an Avalanche pulse generator. And let's do auto set. And let's just reduce the time base. Wow, this is certainly not the waveform I was expecting. From my testing so far, I think the oscilloscope definitely has sufficient bandwidth and update rate to capture the pulse correctly. But I'm a little bit surprised it actually did not capture the waveform correctly, given how well it has done so far. And as you can see that currently we're out of range, the pulse shouldn't have gone down this far, but I'm not sure what is going on here. Now, I think this may be a programming issue, as the hardware is definitely capable. Hopefully I can get some answer from DreamSourceLab on this. Alright, let me show you the built-in function generator. So we can enable the function generator here. Let's enable the output. And you can see we have sine wave, square wave, triangular wave, and sawtooth here. So these are pretty basic signal types. And I think for each of the signal types, we can actually output up to 100 kilohertz. So let's try do that. Let's reacquire the signal. Yeah, that's at 100 kilohertz. And it's very easy to switch the frequency. You can see here, you can essentially tap the digit and use the scroll wheel to actually change the setting here. That's very intuitive. And also we can adjust the output amplitude. For example, we wanted to change it lower. All we do is press that and we scroll it down. So no issues at all. Although the waveform types are pretty basic, but the output amplitude is continuously adjustable up to 3 volts. So let's take a look at the square wave here to see if we can adjust the duty cycle. Yep, you can adjust the duty cycle, which is nice. And let me just briefly touch upon a few other menu items that I didn't show you before. So let's go to more, and you can see here we can also turn on persistence, and you can clean it. And that's the persistence mode. And let's go to File. And the first one you can see, actually this is what I was mentioning earlier to you, is we have the ability to store different sessions. Now, by default, every time you power on, it just stores to that factory setting. And besides booting into default session, you can also choose to boot into the last session. And you can even save the current session, and that will allow you to load the current settings upon powering up. So this setting actually allows you to switch between different settings very easily. And let's just demonstrate here. Remember, when we initially power on the scope, the traces are in different colors. That's actually the default session. So if I go back, if I load that session, you can see that we actually have that pink trace. Of course, we can load the session we just stored. And this is a very powerful feature. And we can also take snapshots of the screen. So for instance, now we're taking a screenshot. What that did was essentially save the screen here. The scope then can be connected to a computer and you can download the image onto your computer. So that's really nice. Let's see what else. Here we can see the disk space we used. And here, here is essentially if you plug into a computer, of course right now it's not connected, but you can use that option to bring up this scope as a mass storage device. And of course you can erase all the user data on this scope. And before we do the teardown, I wanted to show you a few more things. On the bottom of the case, you can see we have these contacts. According to the manual, this is for charging with a dock. On the other side, you can see we have a USB-C port. This is for connecting to your PC and charging. The other port here seems to be reserved for expansion. I will be interested to see what DreamSourceLab comes up as expansion options in the future. Alright, Let's open it up and take a look inside. As I mentioned earlier, this rubber casing unfortunately is not meant to be removed once the unit has been assembled. I was provided a second unit to do the teardown with. As you can see here, I didn't realize it was glued down first and I applied too much force during the teardown. I actually tore the outer rubber casing here. Now, what I didn't realize is that this rubber piece actually is part of the structural element. As you can see here, the entire unit is actually held together by this very piece. Once the rubber casing is removed, you essentially have the LCD sitting on the top, the circuit board in the middle, and the battery tray is at the bottom. You can see this is what the unit looks like once you remove the rubber case here. In hindsight, if I knew it was glued on, I would have been more careful, and I suppose you could remove this rubber holster and reuse it when reassembling the unit. Of course, you probably need to reapply some glue. Anyway, this is how DreamSourceLab managed to get the dimension of this oscilloscope down. And let me just quickly show you the pieces here. So this is the top LCD, and the circuit board is underneath here. And this is the battery tray here. The battery portion is actually the heaviest element in this entire assembly. I didn't want to remove the battery because it's glued onto the bottom of the case, but just by looking at its size, I'd say it's probably between 3 and 5 amp hour in capacity. And here is the LCD screen assembly. You can see we have two of these flat flags coming out. This one is for the LCD and the smaller one is for the touchscreen. As you can see, the touchscreen controller is built in on the flat flags. And because the entire unit is so compact, I think the flat flags cables may have even been custom made just for the oscilloscope, as it doesn't give you too much room to work with. Inserting these cables onto the mainboard is actually going to be pretty difficult. We'll have to see it later. Alright, now on to the mainboard. I have already desoldered these shielding cans from the input channels, so we can see what's going on underneath. Now let's start with this side and zoom in a little bit. Alright, now we zoomed in, you can see both of these input channels. Now they're slightly different on this side of the board. The channel at the bottom is channel 2 and the channel on top is channel 1 here. And if you look closely, you'll notice that channel 2 has more components compared to channel 1, especially in this section here. So I'm not entirely sure what the extra stuff is for. Unfortunately, I don't recognize most of these SMD markings. Also, this is a multi-layer board, and it's not very easy to figure out where the traces go. And if you look carefully, you will see we have a trim pot for each of the input sections. Let's just take another look. This is channel 1, and this is channel 2. By the way, all the high-res photos can be found on my website as well. While we're talking about the input sections, let's take a look at the other side. Now let's reorient ourselves. Channel 2 right now is on the top. On this side, there is a solid-state relay, you can see here, and a mechanical relay and a couple of trim pots by the look of it. One is here, the other one is here. And by the look of it, there are actually quite a few chips here. One of the chips is from analog devices. I'm not entirely sure what that is for though. Again, there are some differences between these two channels, and if you look at the channel 1 at the bottom here, you will see we actually have quite a few of these passives right around this area, and we don't have those in channel 2. So there are some minute differences for sure. The front-end input sections definitely look much more complex than all the handheld oscilloscopes I have done review and teardown so far. And by the way, the MCX connector here next to channel 1, that is for the signal generator output. But there's nothing else I can see on this side that differs between channel 1 and channel 2. So let's turn it around and see what we got on the other side. And on this side you can see we have a chip here, but we don't have one near channel 2. So presumably this is actually an op-amp driving the signal generator output. Anyway, that was just my guess. After the signal leaves the input section, it is digitized by this HAD 1511, which you are probably familiar with, as we have seen this chip used in O1 handheld oscilloscopes. It is a 1 gig samples per second ADC chip, and that is responsible for the specified 1 gig samples per second single channel performance. And because it is shared by both of these channels, the sampling rate would drop to 500 megasamples per second when both channels are enabled. Underneath the HAD1511, this chip here is an ADF4360-7. It is an integrated synthesizer and VCO. It must be working in conjunction with the ADC by the proximity. And you can see here is the FPGA used in this scope. The FPGA used is a Xilinx Spartan 6 FPGA. It is in the XC6S LX16 series. It is a very beefy FPGA. It has 14,579 logic cells, and it is very expensive. It costs over $60 for a single chip in large quantity. Now it all makes sense. The incredibly fast boot up time and the highly responsive UI and a fast waveform update rate, they all can be attributed to the performance of this Spartan 6 FPGA. And let's move down a little bit. You can see down here we have quite a few DC-DC converters in this section, and this is because the FPGA uses multiple voltage rails, and correctly sequencing all the rails can be a challenging task as modern FPGAs have very strict timing requirements. And the chip above that FPGA, this one right here, and that's the DRAM chip, and that's where the sampling waveform is stored. And remember, the DS4T1012 has an extraordinary memory depth at 16 megapoints. And here to the left, we have an STM32H750 ARM Cortex-M7 microcontroller, and that is a $10 component right there. And let's see what else we have here on this side. Next to the MCU, there is a buzzer. And look at the beautiful trace length matching between the FPGA and the DRAM here. And you can also see the trace length matching between the ADC and the FPGA as well. Towards the bottom, near the battery connector, you can see this QFN chip. That is a BQ25601 single-cell battery charging chip. And that's pretty much everything on this side of the board. So let's flip it over. On this side, there are a lot of passives, but we also have these two win-bound flash memory chips here. One is 128 megabit, the other one is 64 megabit. If you recall, at the bottom of the DS4T1012, there is an external battery charging interface, and that is what is going on with the starter board here. You can see these are the contacts for the external charging connector. And this board fits vertically into the notch up here. And that's how it is when assembled. And finally, to the far right, we have this header that is connected to the probe interface and calibration signal output. In fact, I can remove this. This is just a PCB, and you can see here, that is also used as the side of the case. Let me tell you, I'm really impressed by the engineering and build quality of this oscilloscope. The touch interface implementation is one of the best I have seen so far, and the responsiveness of this scope is something you'd be hard-pressed to find, even in a much more expensive one. Sure, there are areas that can be improved. For instance, if the vertical sensitivity can go down to 2 mV per division, or even 5 mV per division, that would be fantastic. And if the intensity grading can be added, that would be even better. But the truth of the matter is, the scope is already pretty darn good. In fact, you will definitely see me using this DreamSourceLab oscilloscope on this channel in future videos. Anyway, I hope you enjoyed the video. If you liked the video, please remember to give it a big thumbs up, and don't forget to subscribe to the channel for more videos like this in the future. I will catch up with you next time.